Yeah, now I'm audible.
Yes, sir.
Sorry, my laptop got switched off. Is my screen visible? I mean, black screen with the logo. Yes or no?
It's visible, sir.
Oh. So we'll get started. Shall we get started? Yeah. So we'll discuss the next important topic, that is called as clock rule. Okay. So till now we were discussing about a conductor, right? About an open surface. For an open surface, how are you going to find the direction of current? Using the right hand thumb rule. So you take the thumb of your right hand, place it in the direction of current and curl the fingers as if you're going to hold it. So the direction in which the fingers are getting curled gives you the direction of the magnetic field, right? Now, what happens if the same conductor is bent in the form of a loop? Then you don't speak about the current flowing upward or downward, rather you speak about the current flowing clockwise or anti-clockwise. Okay. Suppose I take a circular loop where the current is flowing in the anti-clockwise direction. But the current is flowing in the, what happened? Yeah, where the current is flowing in the anti-clockwise direction. Now, if you observe at the top, the direction of current is tangential in this way. At the bottom, the direction of current is tangential in this way. So at any point, if you draw a tangent at that point in the direction in which the current is moving, that gives you the direction of dl vector at that point. Because we know the dl vector takes the direction of current itself, right? Now, if I take a small element here, then what is the direction of dB vector dependent on? dB vector direction is directly proportional to ideal vector cross r vector. So dl vector is in the leftward direction, which is minus I cap cross. What is r? R is the distance vector from the dl vector to the point where you are calculating the field. So this is going to be r vector. So in this scenario, what is happening is dl vector is minus I cap for the top one, and r vector is minus j cap. So minus of minus is plus. So what is I cap cross j cap? It is going to be k cap. So I cross j is going to be k. Meaning, when a current is revolving in anti-clockwise direction, at the center, the magnetic field is directed towards us. So when you see from this direction, it is towards us. That is what k cap is. Now the question is, this plane is emitting the field lines. Out of the north and the south pole that is present, which pole has a tendency to emit the field lines? It is the north pole. So when current is flowing in the anti-clockwise direction, this is anti-clockwise. This is also anti-clockwise. Join both, you will observe the shape of N, so it acts like a north pole. When you talk about a closed loop, the closed loop carrying current in anti-clockwise direction. That is when you're facing that loop, and if you see that the current is flowing in the anti-clockwise direction, you're actually facing the north pole. Okay. So what happens when you go exactly on the back of the board and observe this? When you see it from the front, it is appearing as if the current is in the anti-clockwise direction. When you go to the back and observe, the current will appear as if the current is moving in the clockwise direction. So if it is clockwise direction, obviously when this is going to emit the field lines, that should be in a position to receive the field lines. For the same loop I'm talking about, from the front and from the back. Okay. Now observe at this point, what is the direction of current? This is the direction of current. And what is the direction of R vector? From here, I will join it to this point O. This is going to be R vector. So dB vector in this case is going to be directly proportional to IDL vector cross R vector. So what is the direction of DL vector here? I cap cross, what is the direction of R vector? It is minus J cap. If you take the minus sign outside, I cross J is still going to be K. So it is going to be minus K cap, meaning at the center, the magnetic field is going to be into the plane. So into the plane means it is receiving the magnetic field lines. Which pole has a tendency to receive magnetic field lines? It is the south pole. So this arrow mark represents clockwise. This arrow mark represents clockwise. Join both. It looks like an S. So it is going to be a south. Okay. So what I'm trying to tell you from here is current carrying loops, right? They act as a magnetic dipole. What do you mean by magnetic dipole? They act as a magnetic dipole. Why did I call it as a magnetic dipole? Because for the same current carrying loop, when you see the conductor from one side, when you face the current in the anti-clockwise direction, it is north pole. When you face the current in the clockwise direction, it is the south pole. So both are occurring for the same loop, hence it's a magnetic dipole. Okay, so please make a note of this. Shall I proceed? Okay. So the next important concept that we are going to see is magnetic field on the axis of a circular current loop. So we need to find the magnetic field due to a circular current carrying loop at which point on its axis. Okay. Before that, let's visualize how the circular loop is actually going to look in different orientations. So when I look at a circular loop, when I look at it directly, right? When you take this, when you look at it directly, it is going to take the shape of a circle itself, right? Whereas when I turn it 90 degrees like this and show, then you will only be able to see a straight line, right? It will appear like a straight line. Whereas you neither keep it completely like this nor perpendicular. If you keep it like this, it will take the shape of an ellipse, right? It will look like an ellipse, right? So this is the first point that we need to understand. Here, suppose I take the current to be in this direction, right? If in this scenario, the current is in this direction, okay, if the current is in this direction, when I completely tilt it perpendicular, how is the current? It is towards us, right? So in this scenario, the same situation will become as if the current is towards us, right? Whereas in the third scenario, what will happen is if I tilt it like this, then you will say that the current is in this direction. In all the three cases, what you did is you drew an arrow mark tangential to the surface in the direction of current only. I repeat it. When you look at it like this, if the current is in the anti-clockwise direction, it appears like this, like in the first scenario. If I exactly tilt it perpendicular, then it will appear as if the current is coming towards you because I didn't change anything. See, it's coming towards you. So it will be towards you, right? And what about this scenario? I neither keep it like this nor like this. I keep it in this shape. Then how is the current? It is tangential to the surface. Now let's see what is going to happen at the bottom. So at the bottom, if the current is in anti-clockwise direction like this, right? At the bottom, the current will be like this because it has to take a turn and then come. So it is like this, no, with respect to you, it is anti-clockwise. So at the bottom, it will be in this way. So here, the same current will go in this direction, right? So current is going to go in this direction. So when you tilt it like this, it will be into the plane. So what I'm trying to say is for the same loop, if at the top the current is appearing as if it is coming out, at the bottom it will be as if it is going into the plane. And what about this case? In this case, the direction will be like this. Because this is the direction of current. If I tilt it slightly like this, it will go in this way. Am I clear with this? Okay. Next, we need to understand the word axis. What do I mean by axis of a circular current carrying loop? So if I look at this, for the shape, the center is here, right? The center is here. From the center, if I draw an imaginary line perpendicular to the plane of this, means if it is like this, then this yellow color line is what is going to be called as the axis. So when you look at this direction, how is the axis? The axis cannot be seen because it is this part that you're able to see. So when in this orientation of the circular loop, you will not be able to see it as a line. Rather, you will be able to only see it as a point. So here, it will just be a point. It's not the center. It is axis also. What about this scenario? When I keep it like this, right? When I tilt it in this way, what is it you will be able to see? You will be able to see a line perpendicular to this line. So in this scenario, this will be the axis. Whereas in the third scenario, what will happen? If I keep it like this, it will still be like this, so that some portion you will be able to see, and from the back side, it will start like this. You will not be able to see it like a continuous line of what is appearing here. Meaning, wherever you are able to see the center, at that point, you will be able to see the axis. And there will be one particular place where the center is hidden from you. See, if I keep it like this, you're able to see the center. Backside, you're not able to see. If I keep it like this, you're able to see the center. So the axis will come out from this side as well as it will go from the other side. Whereas when I keep it like this, here you're able to see the center, the backside is hidden. So what will happen is here the axis will be seen like this, whereas at the back, it will be seen like this. So whichever part you are able to see the center, for that you need to draw the axis exactly towards the center. And on the back side, you need to start from the outer surface. This is a very, very, very important point to be noted. Am I clear with this? Right? First, make a note of this. அடுத்து explain பண்றேன். I know complete போல டாபிக் போல. Shall I proceed? So listen. Now we'll get into the derivation. So for the derivation part, what we will do is we will take the circular current carrying loop to be in this orientation. So that let's assume that the current is going in the anti-clockwise direction. So when the current is going in the anti-clockwise direction, this is the side you are able to see. Okay, you are able to see this side. Means this center is visible to you. So how will the axis be? It will be in this way. Now at this point, what we are supposed to do, I'll consider a small current carrying element and we will say that the current is going to be in this direction and the length of this current carrying loop be dl. Now, let me take the radius of the circular loop to be a. Okay. So what is our job? Due to this circular current carrying loop, we need to find the magnetic field at which point? On the axis. So I'll take a point P here on the axis. I need to find. So the only way to find it is using the Biot-Savart law. So for us to use the Biot-Savart law, we need to consider a dl, and from dl you take this distance to be r, and from the center to this point P, let's say that the distance is x. Okay. Now what is going to be the value of magnetic field produced due to the small current carrying element? dB will be equal to mu naught divided by 4 pi into ideal sin theta the whole divided by r square. So let's analyze this equation. Mu naught by 4 pi is a constant. I is the current flowing through this conductor. DL is the current carrying element. The two important points we need to concentrate are what is theta and what is r. So what is theta? Theta is the angle between DL vector and r vector. Right? And what is r? R is the distance from DL to the point. So here r is clear. R is r only, r square. But r can be written in terms of a and x as r is equal to root of a square plus x square. So it's a hypotenuse. Right? Our job is to understand what is the value of theta. Observe, what is the direction of current? Anti-clockwise. So this is the direction of current, anti-clockwise. And this is the axis. From here, you're joining to the point on the axis like this. Right? This is what you're doing. Observe again, this is DL and this is R. For those who are online, check it. This is DL, this is R. Okay. You are seeing in this direction. Okay. Now, if I tilt it slightly like this is DL, this DL, and this is R, this R. Question is, what is the angle between both? You will not be able to judge it when you see from that side. Now, what I'm going to do is tilt it and show. It will be 90. See, it is like this. Okay, it is like this. However you place it. If I tilt it and show, you're able to see that the angle is 90. So in this case, the first important point to be noted is the value of theta is 90 degrees. I hope you're convinced. Right? So take this and substitute it here. Then what will be the value of dB? dB will be equal to mu naught divided by 4 pi into I is I only, DL is DL only. Sine of how much should I write? 90, the whole divided by R square. R square is A square plus X square. It is A square plus X square. Clear with that? Oh. No, root of A square plus X square, the whole square. So square root and square get cancelled. Okay. Now, one point I want you all to concentrate this time. Listen. The point to be noted is dB vector's direction is directly proportional to ideal vector cross R vector. So I'm saying dB's direction, the magnetic field's direction is proportional to ideal cross R. So whenever you do a cross product between two vectors, the point to be remembered is the resultant is there, no? It will be perpendicular to both the vectors for which you do the cross product. How is it going to be? It will be perpendicular to both the vectors for which the cross product is performed. Okay. If that is a scenario, then it is important for me to understand what is the direction of magnetic field at this place. So this is DL vector. So tangential to the conductor is DL vector. From the DL to point P is R vector. So DL and R are already perpendicular to each other. Then the dB vector will be like this. So DL vector, this is R vector. Then dB vector will be perpendicular like this. The complete orientation will look in this way. You can see in whatever orientation you want. You can see that dB vector is perpendicular to DL vector and R vector. It should be perpendicular to both. So in this case, dB vector is going to be like this. But the question to be answered is, why only this direction? Why didn't I draw it perpendicular like this? Why didn't I draw it like this is what I need to answer. Right? So for that, what we will do is we will apply the right hand thumb rule. you need to pay attention. With respect to you, this is anti-clockwise. So place the thumb in the direction of current and curl the fingers. When you curl the fingers, let's say your fingers are going into this and coming out. Okay, at this point, what is the direction in which these fingers are going? They're going upward. So that is the reason why dB vector will be perpendicular in the upward direction to both R vector and DL vector. Makes sense? Right? So this is all about the top DL vector that we have considered. Now what I'm going to do is, I will take another DL vector exactly symmetric at the bottom, but this time, since the current is anti-clockwise direction, if this tangent is in this direction, what will be the direction of the tangent at the bottom? And from this point, I am joining it to this. It is still going to be R. Why is it R? Because they are symmetrically opposite in the first place. And secondly, if you take the surface anywhere from the circumference, you draw R vector, it will be of the same distance. It will be of the same distance. Why is it so? Because you drop all those R, they will take the shape of a cone. It will be the slant height of a cone. So R is basically the slant height of a cone. Are you able to visualize that point? Because this is how the axis is. This is how the axis is, and this is how R is. So R I take anywhere, it is going to take the same distance. Okay. Now, from here DL, this is R. Again, R is going to take the same value, right? The question is, I need to find what is the direction of magnetic field due to this DL vector and R vector. Again, what is the logic? Ideal cross R. So dB vector should be perpendicular to both DL vector and R vector. So how is it going to be? So at the top, the current was like this. At the bottom, the current is in this way. The current is in this way. And where is the point considered? It is considered somewhere over here. It is considered here. So this is DL vector. This is R vector. So dB vector should be perpendicular in this direction. It will be in this direction. Okay. So this is how dB for the bottom DL is going to be present. So the top dB is due to whom? Due to the DL which is considered at the top. The bottom dB is due to the DL considered at the bottom. Right. Now, listen to this carefully. If I take this angle to be phi, okay, I am going to resolve this dB into vertical vector and the horizontal component. So for that, I will draw the dotted lines like this. If this is phi, how much is this angle going to be? 90 minus phi. And you know the fact that dB vector and R vector are perpendicular to each other. If this whole thing is 90 and this is 90 minus phi, how much will this be? So this dB can be resolved into two components as dB cos phi upwards and dB sin phi in the horizontal. Similarly, if I take another angle phi here, then how much will this angle be? It will be 90 minus phi, and how much will this be? It will be phi. Okay. So this dB can be resolved into dB cos phi and another dB sin phi. So how many dBs are there which are contributing to the magnetic field? There are 2 dB which are sin phi which are contributing to the magnetic field. dB cos phi gets cancelled. So the net magnetic field here is going to be equal to 2 times dB 2 times dB sine phi. Okay. This is the overall physics. It's not at over. It's one of the toughest derivations. Okay. So this is the resultant magnetic field at the point P. Now we need to integrate it. Before that, you can copy all these points. Which one? Where will you? Oh, theta is taken here. No? That's why I took a different angle. This is theta. This is phi. Which the இது ஃபுல்லா தான் this is perpendicular no எந்த எந்த ரெண்டு ஆங்கிள் சொல்றீங்க R&DL okay அந்த ஆங்கிளுக்கு இதுக்கு சம்பந்தமே இல்ல here you are using the theta only for this formula this phi you are using to find what are the components இதோட basic similarity if I have to give you remember the equatorial plane derivation. See, in the case of electric field due to an axial electric field due to a dipole at axial point, will you take all these angles into consideration? If you recollect, you will not take because it will be along the same line. One will be in positive direction, one will be in negative direction. Anna, when you do the derivation of equatorial at equatorial point, you will resolve them into components. Adhe resolution. But there is not an equatorial point still. Done. Shall we proceed? So dB net is going to be equal to 2 times dB sine phi, right? So with this, the physics part is over. Now we need to start applying the mathematical part. Observe. So for that, what I will do is 2 times, so dB net is equal to dB net is equal to, you're writing 2 times dB, right? What is dB? It is mu naught by 4 pi into ideal sine 90 is 1, the whole divided by a square plus x square. So it is a square plus x square into what is the value of sine phi? If you look at the triangle here, sine phi is going to be a divided by r. So how much sine phi going to be? Sine phi is so sine phi is equal to a divided by r, right? So a by r means root of a square plus x square. So how much will you write the value here as? A divided by a square plus x square, the whole power a square plus x square, the whole power. How much is going to be the value? Whole power half. Okay, a square plus x square, the whole power half. This is also x only. Okay, so this will be equal to 2 times mu naught. System is slow actually. It's not able to write. So this will be 2 times mu naught. It's not letting me write. Okay, I'll try from the other side and see. Can you tell me how much will the value be? 2 times mu naught divided by 4 pi into ideal into a divided by a square plus x square, the whole power 3 by 2. Because a square plus x square power 1 into a square plus x square, the whole power half. It will be a square plus x square, the whole power 3 by 2. So we'll write and see 2 times mu naught ideal into a, the whole divided by 4 pi into a square plus x square, the whole power 3 by 2. Okay. So this is the value of dB net. But what we need is, we need the total magnetic field. For that, what are we supposed to do? We need to integrate it. Right? So if you observe, let's remember this expression 2 mu naught ideal a by 4 pi into a square plus x square, the whole power 3 by 2. Wrote it? Yeah. So dB net is equal to 2 mu naught ideal into a divided by 4 pi into a square plus x square, the whole power 3 by 2. So if I want the value of B net, what will we do? Integrate on both the sides. When you integrate it, the first thing that you need to observe is you're integrating with respect to what? So look at the differential coefficient. You're integrating it with respect to DL. Now the question is, with respect to DL, what are all the other parameters you have? You have A, you have a square plus x square. A is a constant because it's the radius of the circle. X, though it is a variable, X has no dependency on L. Because as the value of X is changing, is it affecting the value of DL? No. So DL is the only variable in this equation. Everything else is a constant. Take it out. Constant with respect to DL. So take it out of the integral. Then you can write it as 2 times mu naught I into A, the whole divided by 4 pi into A square plus X square, the whole power 3 by 2 times integral of DL. Now, this is where we need to be careful. Okay. Thing is, how many DLs did we consider in this problem or in this derivation? We considered 2 DLs, no? So basically, when you're doing integral of DL, you're adding all the DLs present on the surface. So what I'm trying to say is, let's say I give you a white paper and green paper. So take the white paper and tape it here, and take the green paper and tape it here. So the first white paper is this DL, green paper is the bottom DL. Okay. Like this, what I'm asking you to do is cover this side, cover equal number of white and green papers on both the sides. So how will you do it? White papers, if you start covering it, you will be able to cover only half of the circumference, and the remaining half is taken care by green papers, right? So when you're doing the integration here, you're actually adding all those values in such a way that each DL, that is white individually, green individually, is able to cover how much distance? It is only able to cover half of the circumference. So the limit that you're going to take with respect to DL should be from 0 to half of the circumference, which should be pi into A. You should not take 2 pi A, which is a common mistake that is done. Meaning the number of DLs you consider in a particular problem should be equal to the total value that you need to take. For example, if I had taken only one DL in this problem, I would have considered the limit from 0 to 2 pi A. Since I considered 2, what I did is I did 2 pi A divided by 2. Had I considered 3 DLs, I should have written it as 2 pi A divided by 3. Similarly, if I consider n such DLs, I should write it as 2 pi A divided by n, because each DL is covering how much distance is what we need to say. In this case, each DL is able to cover only half the circumference. That is why you take it as 0 to pi A. Okay. So after this, what you will do is, this will be 2 times mu naught I into A divided by 4 pi into A square plus X square, the whole power 3 by 2. The integral of DL is L itself. Substituting the upper limit, you get pi A, and substituting the lower limit, you get a 0. So pi A minus 0, close it. Pi and pi will get cancelled. 2 will cancel this 4 twice. So you will get the net magnetic field at point P. The net magnetic field at point P comes out to be mu naught I A square divided by 2 into A square plus X square, the whole power 3 by 2, and this is going to be the expression. So this is the value of magnetic field produced due to one circular current carrying loop. Suppose there were n turns. If there were n turns, then the value of net magnetic field would have been equal to mu naught times capital N I A square, the whole divided by 2 into A square plus X square, the whole power 3 by 2. So all that you need to do is multiply this expression with the number of turns. Is that clear? So since they use the word loop, it is only one turn. If they use the word coil, then they should mention the number of turns, multiply the value of magnetic field due to each loop into the number of turns. Is that clear? Make a note of this. Just 5 more minutes. No, you want the next slide? So. Right now. Clear with this? Okay. Now we'll see. So now we'll see some special cases where we need to find the magnetic field due to the same circular current carrying loop at the center of it, right? So what is the magnetic field due to this? It is mu naught I a square divided by 2 into a square plus x square the whole power 3 by 2. So if you take the loop to be present in this way, if you want the point P to coincide with point O, if you want the point P to coincide with point O, then what should be the value of x? The value of x should be 0. Take 0 and substitute it here. What will you get? You will get mu naught I a square divided by 2 into a square the whole power 3 by 2, which is going to be a cube. A square will cancel this. So answer will be mu naught I divided by 2a. So it's going to be mu naught I divided by 2a. An important point to be noted here is when you take the magnetic field due to a straight current carrying conductor of infinite length at a distance a, right, at a distance a, you get the value of magnetic field as mu naught I divided by 2 pi a. Whereas For a circular loop, if you calculate it at center, it will be mu naught I divided by 2a. If you observe, they both appear to be similar. That is the first point. And the second important point is, whenever we think of circle, we associate ourselves with pi. We think of 2 pi a because it's a circumference, right? But a point to be remembered is, when you talk for a straight current carrying conductor, you have a pi. Whereas when you talk about a circular current carrying loop, you don't have a pi. Till now, we use the formula, no? We were using 2 pi a. So going forward, whenever you see a circle, you will not have any pi in the denominator. That is an important point to be noted. Okay. Second, if you want to find at the axial points lying far away from the coil. So when you take the axial point far away from the coil, from the center, if the value of x is more, then what can you say? X is going to be very much greater than a. When x is greater than a, in this formula, if you use b is equal to mu naught I a square divided by 2 into a square plus x square, the whole power 3 by 2. In this place, if you use x to be greater than a, then x square plus a square is approximated to x square. Take that and substitute it here. Then what will you get? You will get mu naught I a square divided by 2 into a square plus x square is x square itself, x square the whole power 3 by 2. X cube. So it will be mu naught I a square divided by 2 x cube. Okay. And the third point is, at an axial point, which is exactly at a distance equal to the radius, meaning x is equal to a. When x is equal to a, b is written as mu naught I a square divided by 2 into a square plus x square the whole power 3 by 2. When you put x is equal to a here, you have a square plus, in the place of x also you have a. So a square plus a square is 2a square. So what is 2a square the whole power 3 by 2? It is 2 power 3 by 2 into a power 3. So 2 power 3 by 2 into a power 3. So when I take that and substitute it here, we get mu naught I a square divided by 2 into a square plus a square the whole power 3 by 2 is 2 into, 2 power 3 by 2 into a cube. So 2 into 2 power 3 by 2, 2 power 5 by 2. And a square will cancel this a cube and a is left out. What will you have? You will have mu naught I divided by 2 power 5 by 2 times a. And this is going to be the question when you calculate at an axial point, which is exactly at the distance equal to the radius of the coil. Okay. These are the three special cases with respect to the same circular current carrying loop. Right. So I can make a note of it. 1 minute. But most of it, there is nothing like many information. Mostly information. There is hard and that's what So this will get added to itself. No, but
Sir, the physics paper was tough for me, sir. How should I prepare for the physics test, sir?
which one is the one I gave?
Sir, your voice is not audible, sir.
Are you talking about the paper which was conducted here?
Yes, sir. The previous test.
Current electricity one, no?
Yes, sir.
Okay. You have to see wherever you made mistake, you have to rework on that.
Okay, sir.
That is only option, right?
Yes, sir.
1 minute.